Hi everyone. In this session, we'll discuss digital design with Verilog part 2. Previously, we have learned many things of Verilog like how to define a module, what are the different types of ports that are available in Verilog, and some basic concepts like what are the different types of operators that are available in Verilog, and what are the different data types that are available. From now onwards, we will start coding in Verilog using different modeling techniques. So these are the contents of this module. First, I will discuss what are the different types of modelings that are available in Verilog. Then in this session, we'll focus on gate level modeling, which is one of the basic level of modeling in Verilog. In gate level modeling, first I would like to show you what are the different types of logic gates that are available in Verilog, which we call as primitives in Verilog. And then I will give some examples using these logic gates, like I will design a 8:1 multiplexer and 1:8 demultiplexer, and I will design a 3:8 decoder with enable and without enable using the logic gates, and I will describe a example of 4-bit triple carry adder using logic gates. Previously, we have seen the 4-bit triple carry adder using flip flops, but now we'll see how to design it with logic gates. So after that, I will discuss some new concept like the gate delays that you can give to these logic gates, and what are the different types of gate delays that you can give. We'll discuss in this, and then we will finally go to the live coding session to explain all these concepts with examples. So let's begin. What are the different types of modelings that are available in Verilog? Basically, Verilog has 4 level of modeling or abstractions we can call. One is switch level, second one is gate level, third one is data flow level, and fourth one is either you call it as algorithmic or behavioral. So the level of abstraction is like this. The switch level is lowest level and behavioral is highest level. What do you mean by highest and lowest level of abstraction? In highest level of abstraction, the more flexibility and technology independent. That means the code that you have written is technology independent and it can be easily portable to any different devices. Same as in the case of, you can take an example of C versus assembly language, right? The assembly language is more of device dependent or processor dependent. The code that you have written will only work on that particular processor. But in the case of C, it is more of generalized thing. The C language code that you have written in one system can be ported to any system. So that is the advantage of high level abstraction, where we call these as high level languages. So the behavioral is one of the high level abstraction that is available in Verilog. Whereas the low level abstraction, switch level, why do we need low level abstractions, right? The low level abstractions are required if you want to design the primitives or the logic gates that are available in Verilog itself. Let's say the logic gates that are available are AND gate, NOT gate, or any gate, NAND gate. These gates can be defined using switch level. What is switch level? It is a level of at MOSFET level. So at this level, the designer has more control of optimization compared to behavioral level. There is an optimization in behavioral level also, but at the device level, the designer can see actually what kind of devices that it is using, what kind of devices that the gates that are used in this design, that can be easily visualized in this switch level. But the problem is the switch level will require lots and lots of lines of code because it is very complex, because every circuit is at down to MOSFETs level. So let's say if you want to design a NAND gate, the NAND gates itself, the two-bit NAND gate itself will require a 4 MOSFETs. So imagine to design a very complex circuit using switch level, it is very difficult. So that is where the high level languages are easy to use. But each one has their own importances and own advantages also. In this particular module, we'll start with gate level, and in advanced topics, I will discuss the switch level and how to define circuits using switch level. We'll discuss in advanced topics. But as of now, we'll start with gate level and then we'll go to data flow level and then we'll see what is behavioral level. So basically, any digital design is done in gate level or higher level of abstraction. Higher in the sense the two other levels like data flow or behavioral, right? And it requires the gate level modeling requires the digital logic design knowledge because you are designing in logic gate level. So you should require the digital logic design knowledge, as we have already discussed this in our basics of digital logic design. So let's begin gate level modeling. So in gate level modeling, the Verilog has logic gates defined as primitives. There are different logic gates. All the basic gates. What are basic gates? Like AND gate, OR gate, NOT gate. These are called basic gates. And universal gates like NAND gate, A and B, NAND gate, comma, NOR gate. These are called universal gates. And some XOR gates and XNOR gates. All these gates are that are available in Verilog. These primitives are instantiated like modules, but they don't require any module definition because the module definition is already provided by the Verilog. So it is like the header files that are already defined in C file. You just need to invoke those and use them as you wish. And one more advantage is, since it is a primitive, you don't need to give the name of that instance also. But in the case of user defined modules, we have to provide user defined names also while instantiating. So that is one thing. And the next thing is the output of gates is evaluated as soon as one of the input changes. So since they are logic gates, they are combinational circuits. The output of these gates is evaluated as soon as one of the input is changed. So let's see what all the different concepts that we have in gate level modeling. So first thing is we'll see how to instantiate the gates in Verilog, and then we'll see truth tables of different gates. These truth tables are different from what we have learned in basic course, right? I will explain how it is different, and we will see different gates like buff gate, buff if gate, not if gate. These are new terms, right? So I will explain these things along with the existing gates like AND, OR, NAND, NOR, XOR, and XNOR. Then I will describe a concept called array of instance, which is very handy when you design very complex circuits. So let's begin gate instantiation. So what does this mean? As I already explained, there are different kind of logic gates that are available in Verilog. So how to instantiate them? The syntax is like this. If you want to instantiate an AND gate with output Y and input A and B. So how to do that? You just need to write AND and then A1, the name of the module, and then output. First you have to give output and then followed by inputs. So this is the way you can instantiate any gates that are available in Verilog. This A1 name is actually an optional thing because it is a primitive. Optional, right? So you can directly write like this also, or and then Y comma A comma B comma C. So what does this do? It will generate a 3-bit OR gate like this, where Y is the output and A, B, C are inputs. Verilog doesn't know that Y is the name of the output. If it defines something like this, NAND of A comma B comma Y. So what does this mean? Always the first one will be the output in case of Verilog. So it will create a NAND gate like this. It will create a NAND gate like this with output as A and then input as B and Y. So you have to define your output first and followed by number of inputs. If the number of inputs are 2, just give 2 inputs. If the number of inputs are 5, you can give 5 inputs as well. So that is about gate instantiation. Now let's see what are the different types of truth tables that are available in Verilog. Now let's see the truth tables of these gates. So first I will start with AND, OR, NAND, NOR, XOR and XNOR. Basically, we know the truth table of AND will look like this, right? Let's say this is A, B, and output is Y. We have four different combinations: 1 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. So the output of AND gate is Y is equal to A dot B, and the output of AND gate is 0 0 0 1, right? But in the case of Verilog, we have two extra signals like X and Z, right? We remember there are four different values that are available in Verilog that are 0, 1, X, and Y. 0 is logic low, 1 is logic high, X is indeterminate, and Z is the high impedance state on the signal. So, how does the truth table looks like in Verilog? Let's take an example of AND gate. Let's take two inputs A and B. The A can have four different values: 0, 1, X, and Z. And B also can have four different values like 0, 1, X, and Z. So I want a function of A dot B. This is my Y. So 0 dot 0 will be 0, right? And 0 dot 1 will be again 0, and 0 dot X will be 0, and 0 dot Z will be 0. Because 0, if you multiply 0 with any value, let's say 0 with 0, it is 0, and 0 with 1, that is also 0. That's why 0 with X will always give you 0. Similarly, the 0 with Z, if you multiply 0 with high impedance signal, the output is again 0. And if you multiply 1 with 0, the output is 0. Then 1 with 1, the output is 1. So this is the basic gate we already know, right? These four combinations. But if you multiply 1 with X, we don't know what is the output, right? If 1 dot 0 will be 0, but 1 dot 1 will be again 1. So the output is X. In case of Z, the output will again X, because the output of these truth tables in Verilog will only constrain X value but not Z value. So remember, the output will always have either 0, 1, or X. Only these three values but not the Z value. So same thing if you apply, don't care with 0, the output is again 0, because in AND gate if one of the input is 0, you can directly write the output is 0. Same thing that happened here also. If one of the input is 0, without checking the other input, you can write the output of the AND gate is 0. Okay. Now X with 1, we know X with 1 will give you X, because we don't know what is the X. Either it can be 0 or 1, so it will be X. Similarly, X with X will also give you X, and X with Z will give you again X but not Z, right? I already told there is no output level of Z in case of Verilog. Similarly, Z with 1 will give you X, and X with X will give you X, and Z with Z will also give you X. So this is the modified truth table of AND gate in Verilog. Similarly, you can write the truth table of OR gate, NAND gate, NOR gate, XOR gate also. So I am not writing the truth table of NAND gate. The truth table of NAND gate will just look it as the inverter of these things. Wherever there is 0, the output will be 1, and wherever there is 1, the output will be 0, and access will stay as it is, right? Similarly, let's take an example of OR gate. We'll do one more time. So the OR gate has two inputs, let's say 0, 1, X, and Z. Similarly, the other inputs has 0, 1, X, and Z. So the output of what is the property of OR gate? X plus Y, right? So if one of the input is 1, the other input, without checking the other input, you can directly write the output as 1. So in this case, the output is 1, 1, 1, and in this case, the output is 1, 1, 1. So 0 plus 0 will give you 0, and 0 plus X will give you, if it is both are zeros, then it will be 0. If it is one of the thing is 1, then it will be 1. So you can write X, this will be X, and similarly this will be X, this will be X, and these two are already X's. So that is about the basic gates AND, OR, NAND, NOR, XOR and XNOR. XOR will be little bit different. Let's see the truth table of XOR. Let's take 4 combinations of input A and 4 combinations of input B. So what is the function of XOR? XOR is if any of the input is 1, then only the output is 1, right? If both the inputs are zeros or both the inputs are 1, then the output will be 0. So 0, 0 will give you 0, this will be 1, and this will be 1, and this will be 0. But in case of XOR, we don't have any predefined thing like if one of the input is 0, then other input can be 0. In case of if one of the input is 0, then output is 0 in case of AND gate. But in case of XOR, there is no such rule. So you have to check with XOR of 0 and X. If you check that, you will get this as X, this as X, this as X, this as X, and everything of these as X's. Similarly, the XNOR will be this will be 1, this will be 1, and this will be 0, and this will be 0. Right? This is the truth table of both basic gates and universal gates. Now let's see the truth table of buffer, and this is the symbol of buffer. Sorry. This is the symbol of inverter, right? So let's see the truth tables of buffer and inverter. The truth table of buffer will look like this. We want buffer. We have only one input, so I am writing input and output. Out. So the 4 values of input are 0, 1, X, and Z, and 4 values are output are. If the input is 0, the output will be 0. That is the functionality of buffer. It will just pass the input signal to the output. So 0, 1, X, and this will be X but not Z, because I told you in Verilog there is no concept of Z as a output of any gates. So that is the truth table of buffer. So for inverter it will be invert of these things. For 0 it will be 1, and 1 it will be 0. This is clear. But what are these two, buff if and buff not if? So let's see the truth table of these two. So the buff if and not if has additional control signal like this. So if you draw the schematic of buff if, there are actually 4 different of gates. One is buff if 1, second one is buff if 0, third one is not if 1, and fourth one is not if 0. So this is the schematic of buff if 1. This is the control signal, and this is the input, and this is the output. Similarly, the buff if 0 will look like this buffer, and the control is negative logic. Control, input, and output. This is buff if 1, and this is buff if 0. Similarly, the not if will look like, draw the normal NOT gate and then add the control signal. So this is not if 1, and similarly the not if, this is not if 0. So these are the 4 different gates. So let's see the truth table of each one of them. So the truth table of buff if 1 will be like this. Now you have two inputs, one is input and other thing is control, right? So the possible combinations are 0, 1, X and Z in case of input, and similarly 0, 1, X and Z. So as I told, this is a buff if 1. So if the control signal is 1, then only it will do the buffer operation. If the control signal is 0, then the output will go into high impedance state. This is the gate at which you can control the output to high impedance state. So it looks like this. If the control signal is 0, then the output went to high impedance state. If the control signal is 1, then it will buffer as it is the signal. But here you see it won't go into the high impedance state, but it will go into don't care condition. This is the major difference from universal gates and these buff if gates. So remember, when the control signal is 0 for buff if 1 or even not if 1, then the output will go into high impedance state like this. And then there is one more thing you need to remember. When the input is 0 and output is x, then the output will not go to x state, but it will go to low state. Similarly, when input is 0 and control signal is z, then again it will go to low state. When input is 1, then it will go to high state. So 1 means high because it is a buffer, 0 means low because it is a buffer. And the remaining two cases are don't cares. So this is for buff if 1. If the control signal is buff if 0, then these two will not change, but 0th case and 1th case will interchange, right? It looks like this: 0, 1, x and z. Let's say this is input side and this is control side. 0, 1, x and z. Since it is a buff if 0, that means it only works when the control signal is 0. So you'll have 0 control signal, then you'll have buffering operation. This will be x, and if you have 1 as a control signal, then all the things will go to z state. Similarly, in this case, it went to z state when control is 0 because it is a buff if 1 gate. And similarly, in xz cases, the outputs are like this: L, H, H, L. Sorry, this will follow as it is, right? L, L, H, H, X, 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 X. Similarly, we can draw the truth table for not if gates also. Let's draw, then it will be very clear. Let's draw the truth table of not if gate. So first I am drawing not if 1. In this case, let's say this is input side 0, 1, x and z. This is control signal 0, 1, x and z. So since it is a not if 1, it only works when control signal is 1. So that is this case. So not if 1. In this case, it will do the inversion operation, right? So when 0, then it will be 1. When 1, then it will be 0. When x, then it will be x. When z, then it will be x. In case of 0, all the things will go to z states. Similarly, the x and z here it will be inverted. If it is 0, both are h's. If it is 1, both are l's. These two are again x and x. So let's see not if 0th case. These are the inputs and these are the control signals. So it will only work when if the control signal is 0. So in this case, it will work as an inverter. So 0 will be 1, 1 will be 0, and these two will be x's. And in one case, it will go to high impedance state. And since it is an inverter, 0 will converted into H and 1 will converted into L. These two will be x's. So these are the truth tables of these gates. But what is the application of these gates? Where do we require these gates? Let's say you want to design a 2:1 multiplexer. So you can do the same thing by using two buff gates like this: buff if 1 gate and buff if 0, because it is already having a if condition inside it. It will only work when the control signal is 1 in case of buff if 1 and when the control signal is 0 in case of buff if 0. So already the if condition is implemented by using this gates. So in order to design a 2:1 multiplexer, 2:1 multiplexer means what? You have two inputs and then based on the select line S, let's say input I0 and I1, based on the select line as the output will either connected to I0 or I1. So this itself is a if condition, right? You are asking whether if the control signal is if S is equals to 0, then connect my Y to I0. If S is equals to 1, then connect my Y to I1. So you require an if statement. So that if statement can be easily implemented by using these buff gates like this. Let me draw the schematic of 2:1 multiplexer using just two gates called buff if 1 and buff if 0. So it looks like this. You have a buff if 1. This is the schematic of buff if 1. This is control. This is input. This is output. Similarly, you have a buff if 0. This is control. This is output. This is input. So what I am doing, I am giving one of the input here. I0 is here and I1 is here, and I am connecting these two control signals as S, and I am connecting these two signals as output. This is my final output Y. You can see the Y will be 1 when this gate will turn on. 1 means Y will be I0 when this gate will turn off, when Y will be uh, y will be I1 when this is turned on, when Y will be I0 when this is turned on, right? So you can implement a 2:1 multiplexer by using just two gates, which is very simple. So after seeing the different logic gates, let's see what is this array of instances. In many cases, you will require the same operation, let's say the same AND gate operation multiple times. So in that case, ideally what you need to do, you have to define, let's say this is my output Y, Y0, Y1, Y2, so on up to Y7, let's say, and these are my inputs A0, B0, A1, B1. Similarly, it will go up to B7, A7 and B7. So if you want to do like this, you have to write 8 different lines, right? Right? End of it has to be small letters. End of, either you can give the name or you don't need to give the name because it is optional, because it is a primitive, not the user defined module. So you can skip the naming thing and you can directly write the combination Y0 comma A0 comma B0. Similarly, and Y1, A1, B1, so on up to end Y7, A7, B7, which will require 8 different lines to get this circuit, right? But you can do in a single line by using array of instance like this. First of all, you need to define the vector or array like this. Y of 7 down to 0, you have Y comma A comma B. Since Y, A, B are 8 bits now instead of single bits, so you define the wire of 8 bit Y, A, B, then write a gate like this and then you can directly write 7 down to 0 bracket open Y comma A comma B. So this is exactly equivalent to this thing. So this is the advantage of array of instances in Verilog. So after we have learned the concepts of different things like Verilog primitives, which are logic gates, and what are the different truth tables of these logic gates, because these truth tables are not conventional truth tables, as they have 4 different value sets like 0, 1, x and z. So we have clearly understand the truth tables of these logic gates, and we have already seen some extra gates like buff if 1, buff if 0, not if 1, not if 0. After having all this knowledge, let's do some examples, then it will be very clear to you how to use these primitives in Verilog. So let's take an example of multiplexer first. So we already seen a 2:1 multiplexer that was implemented using buff if gates. So let's take an example of 8:1 multiplexer and how to do the 8:1 multiplexer using logic gates. So what does then 8 is to 1 multiplexer means? You have 8 inputs and you want to connect it to one of the output. So if the 8 inputs are there, then how many control signals you will require? It is log to the base 2 of 8, which is 3. So you will require 3 control signals. I am writing control signals are S0, S1 and S2, and inputs are I0, I1, so on up to I7, and this is my output. So what does I require? So let's draw the truth table of multiplexer. The output should depend on S0, S1 and S2 control signals. If all of them are 0, I want the output to connect to I I0, and if all of them are 1, I want the output to connect to I7, and remaining cases like this. If it is 0, 0, 1, connect it to I1, 0, 1, 0, connect it to I2, so on like this. You will have 8 different possible combinations, and the output will be connected to 8 different input lines based on the control signals, right? So how to do that? Using logic gates. Let's see the logic diagram of this multiplexer 8 is to 1. So we have 3 inputs S0, S1 and S2. So let's draw the 3 inputs, and we will require the complement of these inputs because the S0 will have both 0 and 1 condition. So I have to have S0 as well as S0 bar condition also. Similarly, S1 and S1 bar, S2, this is S2 and this is S2 bar. Once you have these 3 things, what you need to do? You have 8 different AND gates. You need to connect all zeros to this first AND gate because you want all zeros combination should appear here. So that is, let's take it as a P0 because it is partial output but not complete output. So P0 will be my S0 bar dot S1 bar dot S2 bar. Similarly, P1 will be 0. Let's take this as a MSB, S0 as MSB. This is my MSB, let's take, and this is my LSB. Then this will be 0. This is also 0, and this should be 1. So connect it to 1, 0, then 0. So it is like this S0 bar. So S2, S0 bar, S1 bar, and S2. It is like 0, 0, 1. This is 0, 0, 0 case. So similarly, all the way down to P7. In P7 case, you have to connect all ones S0, S1, and S2. So this is P7. Once you get partial outputs, you just connect through a 8 input OR gate to get the final output Y. This is your final output. So this is the circuit diagram of 8 is to 1 multiplexer using logic gates. So how to implement this in Verilog, we will see in the live coding session, but remember the circuit diagram. Based on this circuit diagram, we will call the logic gates in Verilog using the primitives that are already available in Verilog, and then we will design this complete circuit in the live coding session. So similarly, you can draw the schematic of demultiplexer like this. What is the demultiplexer? So the demultiplexer is the exact opposite thing of a multiplexer. What does it do? The demultiplexer, let's see. The demultiplexer is, it has one input. Let's say data in is my input, and I want to design a 1:8 demultiplexer in which it needs to connect one of the output O1 to O7. Since it is a 1:8 demultiplexer, how many control signals it will require? Same thing, log 2 of 8 will be 3. So 3 control signals S0, S1 and S2. So what is the circuit diagram of demultiplexer? You have an input D in, that is like this, and you have 3 control signals S0, S1 and S2, you need to have both the combination of true value and inverted values like this. And then what you require is the output O1 should get D in. This is my D in. The output O1 should pass to D in when all of these are zeros. S2 will be 0 and S1 will be 0 and S0 will be 0. So if all of these three are zeros, and it will pass D into output. So this is the circuit of uh, demultiplexer. Same thing you have to repeat up to you get O7. In O7 case, the D in is connected and you have to connect S0, S1 and S2 like this, right? So this is the circuit of demultiplexer. We will try to implement this multiplexer and demultiplexer in Verilog while we do the live coding session. But you need to understand what is the circuit behind this multiplexer and demultiplexer. But we have designed multiplexer and demultiplexer, but what are their applications, you can ask. Like there are many applications for these circuits. These are combinational circuits. There are many applications. Let's take an application in communication field. Let's say you have different frequency ranges that are available with you. Let's say you have 2 gigahertz signal, 3 gigahertz signal, 4 gigahertz signal, and 5 gigahertz signal. But if you want to transmit these signals through a single communication channel, then how to do that? You can do by using a multiplexing technique in which you can control by using control signals. By using the control signal S0 and S1, you can control which signal should be passed through, which frequency signal should be passed through this communication channel. That is decided by a multiplexer. Here it is a 4:1 multiplexer. Among the four input signals, it will pass one of the signal at this time by using the control signals. Same kind of applications you can assume, like let's say you have a computer and you have many peripherals that are sitting uh, beside computer. So you have to identify which peripheral should I connect at a particular time. There also you will require a multiplexer thing. And the opposite thing is the demultiplexer will do. Let's say you have a computer and you want to connect the output to four different channels, like let's say Bluetooth speaker or TV or printer or fax machine. You have to fix which path should I pass. The data should be sent to which path. Whether should I send the data to speaker or TV or printer or fax. In this case, you will require a demultiplexer because you have only one source that is coming from computer, and you need to demultiplex it to four different sources like this. So these are the application of multiplexers and demultiplexers, and we'll see the coding of these things in the live session. So let's come to one more example called decoder. Where do we require decoder? We already seen the multiplexer and demultiplexer, but where do we require decoder? If you remember, I have already shown you the decoder in the basics of digital design. Now let's see a three-stage decoder. One basic application of decoder is a row decoder, which is used in memory design. Let's say you have a very big memory array like this. Let's say the number of word lines are 128 word lines and number of columns are, let's say, 16 columns. In this case, if you want to access the data of first row, then you need to have a row decoder, then turn on this decoder. Based on the decoder output, it will access which row you want to write or read inside the memory. So this is the basic application of a decoder. Let's design a 3:8 decoder in Verilog. So what is the schematic of 3:8 decoder? It has 3 inputs and 8 outputs. 1, 2, 3, 0 to 7. Output 0 to output 7. And inputs are, let's say, A, B, C. 3 inputs and 8 outputs. So let's design the decoder. So if you draw the output of decoder, it will be like this. Based on the inputs A, B, C, if all the three inputs are 0, then O1 should be 1 and remaining all the cases it should be 0. And here also it should be all the other outputs should be 0. This is what we wanted in case of decoder, right? If the output is 0, 0, 1, then O1 should be 1 and remaining all things should be zeros. Similarly, if the input is 1, 1, 1, then O7 should be 1 and all the other cases should be zeros. So it will be like this. So how to do that? All you need is just an AND gates like this. You have three inputs A. Similarly, you will require a inverted inputs also B, B inverted, and C, C inverted, and you will require 8 AND gates to get 8 outputs O0 to O7. So if you have all zeros, that means all are 0, 0, zeros, 0, 0, 0, then O0 will be turned on. If all are ones, A, B, C all are ones, then O7 will be turned on. So this is the circuit diagram of decoder. We'll implement this decoder using Verilog in live session. Now let's see one more example, ripple carry adder. In part 1, we have seen the ripple carry adder using full adders, right? 4 full adders. We have designed the ripple carry adder, but let's see what is a full adder using logic gates. So if you remember, the equation for sum and carry out for the full adder is like this. If the inputs are A, B, C in, then sum will be A XOR B XOR C in, and carry out will be A dot B plus C in into A dot B. We have seen how to implement the full adder using two half adders like this. If you have a half adder and half adder, then connect the carry of these two with an OR gate to get a complete carry out, and then connect the sum of these two. Sum of this will be connected to XNOR gate inside this, XOR gate inside this, so you'll get directly sum output, right? We have seen this in the previous module, half adder, half adder, two half adders. If you use two half adders and an OR gate, you will get the complete full adder function. But let's see how to do that using only two gates, XOR gate and AND gate. I'm not using OR gate. Let's see if I want to design the 4-bit triple carry adder only using XOR gate and AND gate, how to do that, let's see. This function sum will require only XOR gates, right? If you remember, let me draw the schematic of full adder using two half adders. Let me draw properly the schematic. So it will be A, B will go to XOR gate. So this is sum 1, and then A, B will go to AND gate. This is carry 1. Apply this sum 1 to carry in C in. Then you will get complete sum of the full adder. Then take this and apply this sum 1, because you need sum 1. This will be, sorry, this will be XOR, not A dot B. So you require A XOR B. This is A XOR B multiplied with carry in will give me this term Cn into A XOR B. I will get here, and then sum these two using an OR gate, right? This is OR gate. Sum these two using an OR gate. This is C1, which is A dot B. So A dot B, and this is Cn into A XOR B. This will be my carry out. But as I already told, I want to implement this thing only using XOR gate and AND gate. So I have to replace this OR gate somehow. So let's draw the truth table of this thing. A, B, Cn. Let's take A, B, Cn. So what are the different possible combinations? 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So in this case, the Cout is Cn into A XOR B plus A dot B. So let's write them. This is A dot B, and this is Cin into A XOR B. So we require an XOR gate operation also. This is I am drawing A XOR B, and this is Cin into A XOR B. So A dot B, let's do 0, 0, 0, 0, 0, 0, 0, 0. This will be 1, 1 because 1 dot 1 and 1 dot 1 will give me 1. Similarly, A XOR B means 0, 0, 1, 1, and then this will be 0, this will be 0, sorry, this will be 1, 1 because 1 XOR 0 will be 1. Similarly, these two will be zeros. So Cin into A XOR B will be Cin dot A XOR B, 0 into 0 will be 0, 1 into 0 will be 0, 0 into 1 will be again 0, 1 into 1 will be 1, 0 into 1 will be 0, 1 into 1 will be 1, right? And 0 into 0, 0, 1 into 0, 0. So the two things are this A dot B, this is first term, and second term is this Cin into A XOR B. If you see the combinations that are available in these two terms, let me write 1 and 2. The combinations that are only available are 0, 0, same 0, 0, 0, 0, 0, 1, and then 0, 0 already written, 0, 1 already written, and 1, 0, 1, 0. So only three combinations are there, right? So what I am trying to say is, for these three combinations, let's say 1 and 2, for these three combinations 0, 0, 0, 1, 1, 0, both OR gate and XOR gate output is same. You remember? They will only differ in case of 1 and 1. In case of 1 and 1, the OR gate output is 1, but the XOR gate output is 0. But this combination is not at all coming in these two equations, right? 1 and 2 equations. So you are freely able to use the XOR gate here instead of an OR gate. So the circuit will be like this. You can replace this OR gate by using an XOR gate. So now the complete circuit of full adder will have only two gates, XOR and AND gate. So now the full adder can be easily defined by using these two gates. Once the full adder is defined, we can define the complete ripple carry adder like this. 4-bit ripple carry adder like this. For a 4-bit ripple carry adder, how many full adders you will require? You will require 4 full adders. So let's draw the 4 full adders. Full adder 1, FA1, FA2, FA3, and FA4. The first one will have carry in and two inputs A0, B0, A1 B1, A2 B2, and A3 B3. It has single bit carry out and 4-bit sum out, right? The 4-bit sum out will come like this: S3, S2, S1, S0. These are the 4 outputs, and then carry of each state will ripple. That is what ripple carry, right? Will ripple from one state to other state. C1, C2, C3, and finally this is C out. So this is the schematic of the ripple carry adder. So we'll draw the schematic using Verilog code in the live session, and we'll stimulate this circuit and we'll see the output of the ripple carry adder. So that is the goal. So let me introduce some new concept called gate delays. Till now we have seen different logic gates, right? But in Verilog or in combination circuits, till now what you are doing, you are applying some input at the input side and you will get some output here. But you are not considering any delay between these two things. It is like the delay is 0. Whenever you will apply input signal, immediately you are getting an output signal. But in real world case, it is not like that. There will always be a delay existing between any gate. Let's take an inverter. Ideally, what you would expect, you will, if you apply 1 here, then you want a 0 output immediately after applying the 1. But that will not happen because the inverter itself is made by using MOSFETs, right? If you remember, this is the circuit of the inverter by using CMOS logic. This is PMOS and this is NMOS. This is input and this is output and this is VDD and this is ground. So ideally what you want, if you have a signal like this going from 0 to 1, then you want a signal like this 1 to 0. But because these MOSFETs will require some time to charge and discharge this node capacitance that is existing here, it will always have some delay associated between input and output. So that delay we are neglecting here. So what happens if you neglect that delay? Your circuit will work functionally properly, but it might fail the timing simulations. Because in real world, when you dump the code inside the FPGA, it will not take the ideal cases, it will always consider the real world cases, because the FPGA itself is made by using MOSFETs, right? So the MOSFETs have some internal delays like this, inherent delays like this. So you have to address the delays. So how, as a designer, what you need to do before doing the implementation, you have to design your gate such a way that you have to assume there is a delay that is associated with each gate. That way, you can modify your circuit from ideal conditions to real world conditions. So how to do that? That is where the concept of gate delays will help you. You can define the delays like what is the rise delay of the gate and what is the fall delay of the gate, what is the turn off delays. So I will explain these 3 terms, and there are different values of these 3 delays. In rise delay, you can have minimum rise delay, maximum rise delay, and typical rise delay. I will explain this, and then I will give you a small example of designing your circuit by using gate delays. So let's see what is rise delay, fall delay, and turn off delay. Let's say you have a signal that is rising from 0 to 1, logic 0 to logic 1 like this. So the rise delay is nothing but the amount of time it will take. Let's say this is my time axis. The amount of time it will take, let's say it starts from 0 and after 5 nanoseconds it is start rising, and after 7 nanoseconds it will completely rise like this. So my rise delay is 7 minus 5, which is 2 nanoseconds. So this is the rise delay. Similarly, the fall delay will be like this. When the signal is falling from 1 to 0, then the amount of time that it is required from falling from 1 to 0 will be my fall delay. And the turn off delay is usually will take this as minimum of rise and fall delay. Okay, so these are the three different delays that are associated in logic gates. So let's take what an example how to define the delays in Verilog. So let's take an example. You can define the delays in three different ways. In first way, this is called one delay method, where if you define an AND gate like this, AND of, this is the symbol to denote the delay. Remember, whenever you want to denote a delay of some nanoseconds, you have to use the symbol of asterisk and followed by number in decimal. Let's say if you want to have a 50 nanoseconds delay, then you have to write asterisk 50. So this will give you a 50 nanosecond delay. So right now I want a AND gate of 5 nanosecond delay. So what I need to define, AND hash 5, and then I will write my logic function as it is, y comma a comma b. Whether you can write the name or not, that is up to you. It is an optional thing. I can write either G1 or G2, whatever gate name I want, or I can leave because it is a primitive. So this is one way. This is one delay method. Since you have defined only one delay, then this 5 will be considered as both rise, fall as well as turn off delay. So what you are telling is the rise time and fall time of this signal y is 5. The other way is you can define both rise comma fall delay of the gate in two delay method. So in two delay method, how to define? Same thing, and hash, and then in bracket you can define, let's say 3 comma 6, and then y comma a comma b. What does this mean? This gate has a rise delay of 3, this is rise, and fall delay of 6. Why do we have different rise delays and fall delays? If you remember, the circuit of inverter is, let's say I am drawing only in the case of inverter. The circuit of inverter is like this, right? This is a capacitor node where you want the output, and this is the input, and this is VDD. If you see, the rise means when input is going from 0 to 1, then output will fall from 1 to 0. So the path of falling is through NMOS gate, and the path of rising is through PMOS gate. Since it has two different paths, and if you properly don't design the inverter to have both rise and fall delays same, then you have a chance of different rise and fall delays. So to emulate those things, even in software also you can give different rise and fall delays. That is the advantage that you got in Verilog. You can model your Verilog logic gates with different rise and fall delays as well, similar to the real world condition. In real world also you can see the paths are different, and maybe because of process variations and all, if you don't design the inverter properly with rise and fall delays, their rise time and fall times will be different. So to emulate that particular functionality, you can use both different values of rise and fall delays. So this is one method, this is second method, and the third method is you can define all the three rise, fall as well as turn off also. If you don't define, then what will happen? It will take the minimum of these two as the turn off. In this case, the turn off delay is 3. Okay. But if you define the turn off also, then it will look something like this. So the turn off delay will be like this, end, and then asterisk. To define this delay, you need to write three values, 3 comma 6 comma 4. So the 3 here is rise delay, 6 is fall delay, and 4 is turn off delay. Rise, fall, turn off, and then you write your actual gate definition, y comma a comma b. Always put a semicolon. I am not putting semicolon here, but in Verilog code you have to put the semicolon, otherwise the syntax error will come. So this is rise, fall, and turn off delays. But what is turn off delay? A turn off delay is defined as whenever the signal is transition from 0 to or 1 to high impedance state, Z state, that is called turn-off delay. Okay. So as I already told, we have three different delays and we have three different values for each of these delays. In case of rise delay, I can define what is the minimum rise delay and what is the maximum rise delay and what is the typical rise delay, right? Why do we have minimum, maximum and typical for rise and falls? Let's take an example of NAND gate using PMOS and NMOS, that is CMOS, right? So I will explain how to draw the gates in switch level modeling, but as of now, consider a circuit like this. It has, let's say this is A, sorry, and this is B, two inputs A and B, and this is my output Y. So it has two different paths for rise as well, right? You can see earlier in the case of inverter, you have only path for rising of output, that is through only one PMOS. But here it has two PMOSes to rise the input. So there is a chance that this rise of input, output, not input, the rise of output will have both the things turned on or one of the things turned on through A gate or B gate, like this. There are different conditions, like there are, let's say, three conditions here. What if the both the things are turned on? Then the rise will be very fast because it is getting current from both the paths. What if only A path is turned on? Then the rise is very slow. What if it turns on to B path? Then again the rise is very slow. And even here also you have different conditions, like what if the path through A is different, consider B, than B. So what I'm trying to say is, if this MOSFET is having W of 5 micro and this MOSFET is having W of only 2 micro, then the path through 5 micro will be fast and path through 2 micro will be slow. So you have different combinations of rise delay itself. So to emulate these things, you have different values. You can define this is my minimum rise delay that I am having at this Y node, and this is my maximum rise delay that I am having at this node, and this might be my typical. Typical means the average value. So if you don't define minimum or maximum, then usually it will take it as a typical value. Like in the previous slide, if I define like this, and asterisk 5, so it will consider as a typical value of rise, fall and turn off delay, but not the minimum and maximum value. It will consider this 5 as a typical value. But if you really want to define different values like min, max and typical, then the syntax will look something like this. So if you want to define typical, min and max, then again let's take a one delay method. In one delay method you can define like this: end of 4 is to 5 is to 6. So what does this mean? The 5 is the typical value. Since we have only defined one delay, so all these three are rise, fall and turn off delays of the AND gate with definition of y comma a comma b semicolon. So the rise, fall and turn off delay will have a typical value of 5, minimum value of 4 and maximum value of 6. Similarly, in the second method, two delays method, you can define like this: end of asterisk 4 is to 5 is to 6, comma 6 is to 7 is to 8. What does this mean? This is corresponds to rise and this is corresponds to fall, and the turn off will be minimum of these two. So the rise will have typical value of 5, rise minimum is 4, rise maximum is 6. Whereas the fall minimum is 6, fall typical is 7, and fall maximum is 8. Fall maximum, fall typical, fall minimum. Understand? And the third one is three delay method. In the three delay method, you can even define the turn off delay like this: end of asterisk 4 is to 5 is to 6, comma, this is not semicolon, just comma, and 6 is to 7 is to 8, comma 3 is to 2 is to 4, let's say. This cannot be 2 because it should be in between these two. So this should be 2 is to 3 is to 4. So what does this mean? This corresponds to rise values, rise minimum, rise maximum. This is rise maximum and this is rise typical. RT, R max and R min. Similarly, this is fall minimum, fall typical, and this is fall max. Similarly, this is turn off minimum, turn off typical, turn off maximum. So these are the different values that are associated with gate delays. So let's see an example. Let's say if you want a functionality of y is equal to a dot b bar plus c. So ideally it will look like this, right? You have a AND gate followed by a OR gate to get value y. So this is your a dot b and this is your c. Let's say you want a delay of 5 nanoseconds for all the rise, fall as well as turn off, and let's say here the delay of 3 nanoseconds. Then the circuit will operate with these delays, will accumulate the delay to get the output of A dot B. It will require 5 nanosecond delay, and to get the output at Y, it will require 3 nanosecond delay. It will be very interesting if you simulate this circuit and see the timing diagrams. We'll do that in the live coding session, and I will explain how does the output waveform will look like with different input combinations of ABC. So thank you.